So we're moving back to simulations with Renyue on the coevolution of black holes and galaxies.
Thank you. Okay, many of you may have this religious belief that the observed correlation between black holes and bulges are due to some internal regulation by the black holes. So my goal is to make you doubt this religion after this talk. So there is a intriguing correlation between black holes and bulges, indicated by the schematically by the black solid curve at the upper branch. So that's well known. But not well known is that that relation extends to lower mass bulges. And when the division occurs at about 3 times 10 to the 10 stellar mass bulges. Above the division point, the black hole mass dominate. Below the division point, the nuclear star cluster mass dominate. So what's listed is some of the observational papers that demonstrate this relation. So in this case, the compact massive object is the sum of black hole and nuclear star cluster. Now, what can we learn from this universal extended relation over 4 decades in stellar mass? So right there, so let's express this relation as the sum of black hole and nuclear star cluster is proportional to this bulge mass, where alpha is about 0.2%. Let's express the feedback. That's assuming at the outset, say the central nuclear object, either the black hole or nuclear star cluster, is regulating the growth of the bulge. Here F is some coefficient. That means a big portion of the bulge gas gets expelled by the central nuclear object. And here E black hole and E nuclear star cluster are the feedback coefficient per unit mass of the black hole or nuclear cluster respectively. And the beta, sigma here is the vast dispersion of the bulge, whereas the beta describe whether it's momentum feedback equal to 1 or energy feedback beta equal to 2. Okay, now given that this relation is extended and the slope doesn't even change crossing the division point, then the only logical way you can understand is the feedback per unit mass of the nuclear object is equal across the division. In other words, E black hole must be equal to E nuclear star cluster. Now, if that were the case, then if you go back to this lower branch, since here the amount of stars in the bulge, same all the stars as the stars in the nuclear star cluster, dominate the nuclear region by a factor of 500. Therefore, it's illogical to assume that the nuclear cluster, the star cluster, can exert feedback to regulate the bulge growth. By extension, if that were the case, then the feedback from the supermassive black hole would be subdominant compared to the stellar feedback from stars in the bulge itself. Then you ask next question. Okay, can the stars in the bulge regulate the bulge itself. Let's express that statement by this simple equation. You can cancel these two. And this turns out is supported physically either in the momentum conserving phase, in the momentum driving phase, beta equal to 1, or energy driving phase, beta equal to 2, as demonstrated in this paper. Therefore, bulge self-regulation, if required, will be physically supportable and self-consistent. However, if that were the case, then under the assumption that since the nuclear cluster and the bulge, they're both made up of stars, then the efficiency must be the same, then the nuclear cluster will be self-regulated. Then the correlation between the central massive object and the bulge was then required that the mass loading factor for the black hole is the same for the nuclear star cluster. That's a very fine-tuned outcome. So that's not satisfactory physically. So then, where does this correlation come from? And we suggest it's simply due to gas supply rationing. In other words, the amount of gas that reaches the nucleus region, either feeding a black hole or nucleus cluster, has a fixed proportionality averaged over the cosmic time to the amount of gas landing in the bulge region. Now, I'm going to use the remainder of the talk to test the scenario using simulations. So we have a set of simulations we call LOTS simulation, Old Chinese. The name actually, old is in the name, the old master. Standing for large-scale adaptive measure from omniscient zoom-in cosmological hydrodynamic simulations. It's by far, it has the best combination of sample size. We have a few thousand galaxies with stellar mass more than that. And the maximally resolved is maximum resolution. Not everywhere resolved that, but maximally in some locations at the tens of parsec. So that allows us to say some meaningful things on galaxy formation, since we are almost touching the molecular cloud's core scale. We have all the relevant microphysics and have dense output data, so we can track history of each individual galaxy. And we include supernova feedback, but without aging feedback. So we can test it without aging feedback, see if you can produce the correlation. Now, resolution is high in the standard, the cosmological type simulation, but it's not sufficient if you want to track the feeding into a central black hole. So we made some simplification and trying to capture the physics. So here, the four assumptions we have made. Well, this is not assumption, this is just the simulation tool we have. Then assumption number one is that the angular momentum distribution in terms of mass, so mass less than specific angular momentum J, is proportional to J. And this is the standard Mastell disk you'll get. And that was what I set out to do. It was assumption in my mind. Then I started searching for literature. I found Phil and the area quartet had a couple of nice papers. Actually, I've done very high resolution simulations with less than 0.1 parsec resolution zoom in, looking at this particular problem of how the gas feed the black hole. And turns out, in almost all the zoom in simulations, this is borne out. The deviation from this slope is less than about 20% in the worst cases. So that is assumption we put in. Then the second assumption, just standard observation. There are many variations, but it won't change the conclusion whether you change this to 5, for example. And then the last assumption is sort of trying to take into account the black hole accretion physics. That is, for accretion disk, there is a radius, a threshold radius, where the tone rate Q parameter is 1. Interior to this radius R0, the value is about 0.1 to 1 parsec, that the Q is greater than 1. Therefore, the disk is stable, whereas exterior to this R0, this Q is less than 1. Meaning that the outer part of the disk will be unstable to star formation. Therefore, will be consumed largely by star formation. Whereas the gas interior to this radius will be able to accrete. And the assumption here is the gas within that radius will be added to the black hole for each episode of a gas accretion. Given that, then we can compute the library within 1 kiloparsec, just to remind you that our resolution is tens of parsec. So we have confidence that the mass measured within that radius and the angular momentum, the mean angular momentum within that radius can be measured reliably from simulations. And then with these 3 assumptions, these answers here, and we can derive how much gas will be located within this R naught, and which we can calculate this. That's because you made this assumption here. And therefore, you can compute the black hole accretion rate, okay? So which is the mass you can measure here. Sorry, this missing subscript here. And here is the dynamical time you can measure from simulation. The simulation actually follows star formation directly. So we can derive the star formation rate directly without making any of these assumptions. But the black hole feeding rate is derived based on these assumptions. Most of them are well supported. The R naught here, depending on these various parameters, adding rate, black hole mass, Mach number, and so on, this opacity has variation, but as you notice, these powers are pretty weak. So it doesn't vary a whole lot. So given that, here I just give you 4 random example galaxies. We trace the history, so from high redshift to low redshift, and this last point we looked. And here, what's part here is, this is the, I lost track. Oh, okay. So the ratio of the black hole feeding rate over the star formation rate times 500 is the red curve. And the blue curve is the accretion rate. So the red one is the ratio. And it's multiplied by 500, meaning that if this ratio is about 1, then the observed Lagrangian relationship will come out naturally. Okay? But these are just 4 random examples. You can actually do better. Since we have hundreds of to thousands of galaxies, depending on redshift, you can actually do the number averaging. Here, I break the sample up into 3 different stellar mass ranges, from low to high. And they don't vary a whole lot, but there's a trend that is, when you go to higher redshift, that this ratio has some modest increase, but within a factor of 2 to 3, as you can see. So this means that, but if you see average over the history of individual galaxy and then take a ensemble average over galaxies, as you can see, it comes up naturally at this relation. So if you have data in the future, be able to measure the black hole mass to the Bulge mass ratio, and the prediction here is that that ratio will increase slightly by a factor of 2. Okay, so I spent the first part of my talk trying to argue that the internal self-regulation by black hole of the spheroid or the Bulges is physically illogical, because various ways you can argue about it, but you come to the conclusion that it requires a huge amount of fine-tuning to possibly get to that relation based on internal regulation. In other words, the internal regulation, the feedback is there, but it cannot be regulating that ratio. And then we show with ultra-high resolution cosmological simulations that rationing in gas supply to the nuclear and the Bulge regions give rise to the proportionality about 0.2%. And the conclusion we get from here requires a few assumptions, but all of them seem quite plausible, and some supported by high resolution simulations already, and most of them have a good observation evidence for. And the coevolution between the activity of the supermassive black hole and the bulge, in other words, the accretion activity and the star formation rate can only exist on time scales longer than tens of probably 100 million years or longer. On small scales, small time scales, the correlation will be mixed. That's because the accretion disk physics determines its own time scale, how gas gets accreted. And that seems to be consistent with extant observations. Now, you might be puzzled because we do see radiation from black holes, from active agents. We see waves coming up from broad emission and absorption line regions, and we see radio jets coming out. So all these exist, but they do not provide organized, regularized feedback on the bulge from the black hole for every episode. But rather, they collectively feedback these energy, momentum, radiation to the surroundings, including the interstellar medium and circumgalactic medium and intergalactic medium. In other words, they control also wind direction. They basically reduce the overall amount of cold gas can return back episodically into the galaxies, okay, to power a star formation in episodic fashion, as well as the accretion event in the nuclear region from this cold gas. But every time you have a feeding episode, that the angular momentum distribution is such that it hovers around about 0.2% of the gas reaching the nuclear region versus the one outside nuclear region but within the bulge. And the galaxies experience multiple such episodes across its history over the cosmic time. And so this cosmic time smoothing or averaging and multiple episodes in the end give you this seems a very tight correlation between the supermassive black hole mass and the Bulge mass.
Okay, thank you.
Thank you.
Running a bit early, so we have time for questions.
Okay.
Maybe I can just talk around it. As you black hole? Have you looked at the angular momentum that you predict for your black holes? Have you looked at if they're maximally rotating or if they're oscillating up and down?
So you're saying if I were to track this gas accretion onto a black hole, see how they add up over time?
That's right.
I will have no ability or confidence to make a statement on that at this time, because that require I think there are evidence that observationally already you have inclined ongoing gas disk versus stellar disk and so on. So unless you're assuming every accretion is coplanar, okay, even in that case, current resolution, at least mine, is not adequate. But it's averaging over time. But in addition, I'm not following the black hole mergers. So they will totally screw things up. So I cannot give you any answer on that.
Can you comment on how, in your simulations, the black hole mass to either the stellar mass or sigma 8, the sigma of the stars, how that changes with cosmic time?
You must be sleeping. Okay, so here's the relation.
How does this compare to observations?
Well, no. I mean, here's 500. So that means the black hole mass over the stellar mass is 0.2% ratio.
Do observations agree with this?
Yeah, I think Sandy will agree with that. It's a 0.2, right?
I think Joel's question is whether there's evidence for an evolving ratio.
Yeah, the ratio goes up.
In your model, I think his question is, do the data support that?
Yeah, so I was saying that future data, because I wasn't aware of reliable data at high redshift. Because I think there's some data by Branford, somebody look at here redshift 1-ish, but I mean, you have, here's overlap kind of. Not much difference here from low redshift. Does that answer your question?
There's some reports of black hole masses that are much higher than this kind of ratio at high redshift. I don't know how serious you take them. No, but going out to even higher.
Yeah.
The ratios of orders of magnitude higher.
This is line-based. I heard opinions that you shouldn't bet on it.
So here,
Yeah.
when you compute accretion rates based on the estimate of gas that is supposed to get down to the accretion disk,
Yeah.
right, and then divided by this dynamical time
Yes.
scale. But in principle, a lot of gas can be lost from the accretion disk in winds. So could that introduce some different normalization in the ratio of black hole mass versus galaxy mass, or how does that?
What I can
into the
imagine,
picture?
I mean, we're not following in brute force, of course, at that scale, okay, is that there'll be a random feedback. You can imagine their wings blowing things, things got randomly splashed and pushed out. But these just sort of increase the dispersion slightly, okay? But won't change the ratio from, 1 to 500. In one case, maybe 0.5 to 100. In the other case, maybe 2 to 500. So, but they might affect things proportionally in terms of feedback. As the previous talk indicate that the energy from supernovae probably is more powerful to drive wings because they're subject to less feedback, less cooling.
Hand it over to him afterwards.
Hi. I have a question regarding the initial argument you are making about the ill-posedness of the... why don't you consider that inside the nuclear star cluster there might be a black hole, and that the feedback comes from the black hole? So you have the same E epsilon black hole all the way through the entire relation, and the feedback comes only from the black hole, and the nuclear star cluster is just the cradle in which the supermassive black hole can grow when it's smaller than some threshold.
Yeah, but that is not possible. That's because the nuclear cluster, the sum of NSC and the supermassive black hole follows this trend. I mean, it's not as nice as this, but basically it's the same trend. And And there's evidence that in this red branch, the mass of the nuclear star cluster dominate the supermassive black hole mass. So in other words, if you just draw this line black, continuation of this black line, then will be steepen. So then you have to make additional assumptions. Somehow the feedback stream changes shape along this division line in order to revert back to this universal correlation between CMOs and the bulge. Does that make any sense to you?
No, what I'm saying is that you have some kind of logical reasoning,
Yeah.
but it's not that logical because you have so many vision parameters that it's not that clear.
Okay.
Where's my parameter? I mean, I only have this simple expression.
One more question.
Okay, now look, empirically I would say what you're saying is qualitative quite what we're seeing, both at low and high redshift, in the sense that, number one, you bring a lot of gas into the nucleus, and if your goal is to bring into the black hole, sorry, you'll produce some stars. And that is seen, obviously. And so I think in that sense, if there's feedback, it can come from both. And indeed, to the extent you can measure the M dots, which is not trivial, of course, I would say it's correct. At both low and high redshifts, as far as I know, the mass loading factors for star formation and AGN feedback are, on the order of unity or 1 to 3, so they're comparable, just like what you like. There is a difference, though, and that is the velocity of the outflow, right? So both low and high redshift, the star formation feedback is a few hundred kilometers per second, which is less than or barely comparable to the escape speed of the system, whilst the outflow rates of the AGN feedback is much higher. So that could make a big difference in the end, of course, how far you can push the material out.
I think I agree with all your statements. But then I think the key question is, if you sum up the energetics, individually you might have stronger wings in some cases. But if you take into account the duty cycle, the abundance, if you sum them up, then you ask how much energy is actually getting up to the intergalactic medium or circumgalactic medium in the form of supernova-driven wings versus the AGN-driven wings. Maybe somebody has done the exercise. I'm not sure.
I was already averaging over the AGN feedback up and down. Okay, so these are not AGNs; these are galaxies which have pretty massive outflows. So you average that duty cycle, and the M dots come out.
Okay, I think I have worked on this quite a bit too, so I want to make a short remark too. I think the one thing I have learned in that business, there's probably not one explanation for this damned M-sigma relation, and I think it's very worthwhile reading again the Ho and Cormandy annual review article, who basically makes this point extensively, that there are probably many things contributing, and I think what we had here is a discussion between supply limited and feedback limited, and I think it's both at work. And sort of at some stages, once the black hole gets too massive, the feedback gets too violent, and the black hole just doesn't go anymore. So it doesn't mean that the whole M-sigma relation from the small black holes to the large black holes is actually set up that way. But I think what we're seeing is just a range of processes, and that's the reason why we are arguing now for 15 years about this, or 20 years nearly. Sort of, there is a range, and I think it's probably both. At some stage, it's supply limited, but once the black holes get too big, they shut themselves off too. So I think there's a combination of both, and that's sort of my view in it. And
well,
as I'm the chair, I'm relieving you now for coffee, and we discuss it over coffee.
Okay.